Hi, I'm David, and today I'll be talking about our work on optimizing rigid scene flow from 3D point clouds without labels, specifically in autonomous driving settings. So the problem we are trying to solve is, given a pair of consecutive 3D point clouds, to predict the scene flow between them without using any labels. And scene flow is defined as a vector field denoting the motion of every point in the scene, or the 3D counterpart to optical flow. Recently, there has been significant work towards self-supervised scene flow estimation on point clouds. These approaches use the nearest neighbor or chamfer distance as the primary loss function in conjunction with regularization terms. Additionally, there have been successful offline optimization-based approaches such as neural scene flow prior, which trains a neural network for each scene, using it as an implicit regularizer. Our approach is based on the observation that scenes are often composed of independently moving rigid objects, especially in autonomous driving settings. Instead of pointwise motion vectors, we parameterize scene flow at the object level as a set of bounding boxes and rigid transformations. This gives us a lower dimensional optimization space and constrains our flow to be physically coherent. We then solve for these parameters by optimizing them over the nearest neighbor distance using gradient methods. However, the nearest neighbor distance is non-differentiable with respect to the bounding boxes, so to make them differentiable, we soften their edges using a sigmoid approximation, as illustrated here. In our true loss function, for each box, we differentiably select the points inside it and transform them using the box's transform and the ego transform. Then we compute the nearest neighbor distance between the two transformed point sets in the second point cloud. Lastly, we weigh the two nearest neighbor distances by c and 1 minus c and compute the sum, where c is the confidence parameter for the box. If the nearest neighbor distance is smaller when using the ego transform, then the points in the box likely belong to the background and the confidence will tend to 0 to minimize the loss. On the other hand, if the nearest neighbor distance is smaller with the box's transform, then the points are probably part of a moving object and the confidence will tend to 1. Here we show our optimization in action. The boxes are initialized in a grid with 50% confidence. Throughout the optimization, some of them converge around cars and become red with high confidence, while others converge around the background and become purple with low confidence. To convert our optimized boxes and transforms to pointwise scene flow, we first apply some post-processing by pruning empty boxes, applying non-max suppression, and assigning points to the most confident box therein. Then we compute the flow for each point by transforming it with our box's rigid motion, or the ego motion if they aren't in a box. We evaluate our method on the KITTI Scene Flow benchmark in both the stereo and LiDAR domains, as well as the nuScenes dataset. Our method achieves state-of-the-art endpoint error on nearly all datasets. Additionally, because our parameterization includes motion segmentation masks and ego motion, we also evaluate these predictions on stereo KITTI and semantic KITTI, where we achieve compelling results. Here we visualize our endpoint errors on a scene in KITTI against the other optimization methods. We also show the bounding boxes generated from our method. While other methods either have noisy predictions or struggle to find moving objects, our method produces extremely accurate predictions in both the foreground and background, although we do miss an object in the latter setting. In conclusion, we propose a novel method for optimizing object-level rigid scene flow without any labels. Our method achieves state-of-the-art accuracy by constraining the scene flow to be physically consistent, and simultaneously detects moving objects and computes ego motion without any labels. Thanks for watching, and please refer to the paper for more details or contact me if you have any questions.